Okay, so first, anybody have any homework questions? I want to show you a new way to think about beam calculations. We're going to do more beam calculations as the class goes on, mostly because we're going to get into internal loads in beams. But I want to show you that there's sort of an easier, faster way to do it than filling out the full table. And then I'm going to show you how if you expand that idea to 3D, it can give you sort of a sanity check on your answers. It's not as fast a way to do the calculations, so I don't think you should like use it for your calculations, but you can at least check the signs on all your components and stuff. Okay, so here's a faster way to calculate reaction loads on 2D beams. I wouldn't really use it for anything except beams. And what do I mean by a beam? So I think the part of a beam that everybody would get right, if I made you guess, is it's something that's a lot longer than it is wide or whatever, right? It's a long thing. But beams really refer to the way that it's loaded. So a beam is something that has loads on it besides just axial loads along the length, either tension or compression. Okay, so if you have, let's do a problem, and I'm going to use another distributed load because why not? We're getting practice on those. So let's say that we have a distributed, okay, so here's the beam. Let's say we have a pin joint in the middle. And a roller at the end. And we have a rectangular distributed load acting on the right half. So let's say this is 1/2 meter. And this is 1/2 meter. And this distributed load has a magnitude of 500 newtons per meter. Okay, well, I'm going to do a free body diagram. In my free body diagram, I'm going to represent that distributed load as a point force. So I'm first going to figure out where the centroid is and what the area is. The shape is a rectangle, so the centroid is going to be right in the center. Okay, we don't care about anything except the x position because of the because you can move that force along its line of action. And then the area of that shape, we have a length of 0.5 meters. We have a height of 500 newtons per meter. And so the area is 250 newtons. So Newton's second law. There's the beam. We have a pin joint at the center, so that applies an unknown force vector. I'll call that RA. And then we have an upward force from the roller. I'll call that RB. And, well, I didn't give a mass, but let's give a mass. So 1 meter long, let's say that's 20 kilograms. So then we have a force down of 20 times 9.81, 196.2. And then the last force acts at the, that quarter point, that 3/4 point, halfway between the center and the right end. And the force is 250 newtons. Now, this is a rigid body, so of course you always can write out the table and do things that way. You always can do that. But notice that we have a case where all of the row vectors, all of the row vectors are just going to be horizontal, no matter where we're looking at. And that's because we're ignoring the thickness of this beam. Okay, so I'll make this the about point. And then, so I'll do Newton's second law, and then you'll see it on the, so I'm not going to write the table. I'm going to do Newton's second law, and then when I go to the moment equation, I'm just going to figure out that horizontal distance from the about point to where the force is applied. And then I'm going to think whether that moment would cause a clockwise or a counterclockwise rotation to come up with the sign. And I'm just going to do it that way. It's a little more like probably the way you did it in physics. Okay, so Newton's second law. So we got RAX, RAY plus 0, negative 196.2 plus 0, negative 250 plus 0 RB is equal to zeros. 1, 2, 3, 4. Okay, so that looks good. And then the moment equation. So for each force, we're just going to figure out the horizontal distance from the about point to the force. And then based on what direction the moment arm is and what direction the force is, we're just going to think of the directions of rotations. So, okay. First, I'm going to write it like this. You don't have to do it as plus or minus. You can just think about what the sign is. But, okay, for the force RA, that's at our about point. So the row vector is 0. The force vector is, and in this case, we have, two different components here. The only component that's going to, on a beam, that's going to produce a moment is the vertical component. You see that? Any horizontal forces are just acting right along the line of that beam, and they're not going to produce any moments. So I'm going to ignore all the x components. Again, this is just because it's a beam. It's just because it has 0 thickness. So we have 0 times RAY. And that goes away, so we don't have to worry about it. Same thing's going to happen with the weight. So we have plus or minus 0 times 196.2. Then the 250. So we have plus or minus. What's the moment arm for that force? Yep. So plus or minus 0.25 times 250. Notice I'm putting all of these forces and distances in as positive, and then I'm just intuitively looking to see what rotation it would cause. Would this produce a clockwise or counterclockwise rotation around that hinge? Clockwise, so this is negative. And then we have plus or minus. Now we're on the force RB. What's the moment arm for that? 0.5. And would that force cause a clockwise or counterclockwise rotation? Counterclockwise. This is equal to 0. So this one goes away. And what we have is we get 0.5 RB is equal to 62.5. And so RB is equal to 125. And then calculate RA from there. It's 0 for the X component, you can see. And the Y component, can someone calculate that for me? -321? Yeah. 0.2. Okay. Okay. You can also use this idea as a sanity check, you know, just like a quick, don't be nervous about your answers kind of thing. On the signs of your cross product components, you know, when you're computing the moments. And you can do this by breaking up the force vectors into components. Okay, so here's a 2D example. Let's say we have a pin over here. And actually, forget that. Let's just make this an about point over here. Okay. And let's say that we have a force vector applied here at an angle of 30 degrees. Let's say this length is 0.3 meters and this length is 0.6 meters. Okay. Well, if you think about the table, like let's do it the way that we normally do rigid body problems. So we have this one force. The rho vector is -0.6, -0.3. The force vector, oh, I didn't give a magnitude yet. Let's say that's 100 newtons. So the force vector is 86.6 and 50. And then the cross product is, so that's -30. Can someone calculate that for me? Positive 4.02? Okay. And so now if you think about it as components, so there's your about point. Now we're going to think of this as two separate forces. One has a magnitude of 50 like that. And the other one has a magnitude of 86.6, like that. And so the moment is equal to plus or minus, the 86 has a moment arm of 0.3. That's a counterclockwise moment, so it's positive. The 50 has a moment arm of 0.6 and a force of 50. And around that about point, it produces a clockwise moment. And so, I said you can use this as a sanity check. In this case, those two are close enough to each other that it's kind of hard unless you do the calculation. But a lot of times you can look at this if there's, and just say, okay, there's one force component here or something. You can see that it's positive or see that it's negative and just quickly compare that to your cross products. You don't have to do that, but it's one of many good practices in the cases when you really need to get a problem right, In a class, you don't usually really have to get a problem right, but in life, you do kind of, Yeah.
I missed how we got the row vectors.
Oh, yeah. Well, so it's all you're doing is you're talking about in this way of doing it, right?
Yeah.
Yeah, just so it's the distance. So you're trying to get the perpendicular distance from basically the line of action of the force.
Okay, so that's just using the equipolant idea.
Yeah, that's right. So, right, so this distance to that green line is 0.6, and let's see. The distance from the about point to the blue line is 0.3.
Okay, and then one is clockwise and the other is counterclockwise.
Right, exactly. Yep. Okay, how about a 3D example? So let's say we have a plate. And let's put our about point here. And say we have a force acting at the corner straight down. Let's say that's 100 newtons again. And our distances here are 0.3 and 0.6. Why not? Bless you. Okay. Well, I have to give a coordinate system. So let's say we'll go X, Y, Z. Okay. Well, the way that I recommend doing your calculations is to write out this table. And so the row vector, you have to go 0.6 in the positive X, 0.3 in the negative Y, 0 in the Z. The force vector is 0, 0, negative 100. And so the cross product is 30 for X, 60 for Y, and 0 for Z. So now let's think about it using this other way of thinking about it. Break this up into components. In this case, there's only one component. And now think about how this thing will produce rotations about each one of these axes. So perpendicular to the x-axis, we're going to have plus or minus. What's the moment arm of that 100 Newton force in causing a rotation about the x-axis? Can you see that?
130.
That's right. Times 100. And would that make it rotate clockwise? Well, now we have to think, I guess, in terms of the right-hand rule. Would this force make it rotate in the positive x direction or the negative x direction?
Positive.
Positive. So we want the positive here. So this is 30. How about the y now? My. So we have plus or minus. For a rotation about the y-axis, can you see what the moment arm would be?
0.6.
Yep. So 0.6. The force is 100. And would that make it rotate in the positive y direction or the negative y direction?
Positive.
Positive. And that's 60. And then for z, plus or minus, what's the moment arm that this force produces about the z-axis?
0.
0. Okay. How did I get those moment arms? Anyone confused about that? I guess the way to think about that is think of extending the axis all the way through the about point and making it a line, and you're finding the distance, the perpendicular distance of that force to that axis. So so if we're doing the rotation about x, think of extending the x-axis. That's not x. Okay, think of extending the x-axis through that about point. Okay. Now that 100 Newton force, it's like, how would this make the thing rotate around that axis? Okay. How would that 100 Newton force make this object rotate if you had like a pin joint or a hinge along that axis? Yep.
What do you mean when you say that it's rotating with the positive or negative?
Oh yeah, right-hand rule. Put your thumb in the direction of the axis, and your fingers are in the direction of the positive rotation.
Okay.
So you can also think counterclockwise and clockwise if you imagine looking straight down the axis. Okay.
I'm taking physics too, so it's like all the right-hand rules can get really confusing.
Yeah, I know.
And all that kind of stuff. So.
I was afraid you were laughing like, I'm not paying attention to this. This is stupid.
No, I was just thinking like, dang, right-hand rule.
Oh, yeah. Well, your thumb, okay. Right-hand rule is always a relationship between a vector and a rotation.
Right.
Okay. So your thumb is the axis, and your fingers are the rotation.
Okay.
So this thing is rotating. This force, if we're considering the rotation around the x-axis, is rotating
right.
this way. So if you do that with your fingers, your thumb is pointing in the positive x direction.
Okay, that helps a lot. Thank
Okay, great. So, any other questions?
Are the row vectors always perpendicular, or is that just because we have our axis?
In this case, since we're going component by component, yes, they're always perpendicular. So you can just Yeah, so there, you don't have to do any cross products with this. You can just find that distance from the axis to the force. Okay, so let me draw the other two axes and you can see how it works for, is everybody able to make sense out of this rotation about the x-axis? Okay, so now let's do it for the y-axis. So the y-axis, extend that through the about point. And think, would that 100 Newton force cause a rotation about a hinge? If, you know, if that dotted line was a hinge? And yeah, it would cause a rotation. The moment arm is 0.6, because that's the distance from that hinge to that force. And now think about the direction. This force would cause a rotation up the back, down the front, you know? So do that with your fingers, up behind the axis, over, down the front. Your thumb's pointing that way, so that's a positive Y rotation. Yep.
So the direction that your thumb faces when you're doing right hand rolls will depend on rho?
It is dependent on rho, yes. And it's also dependent on the force direction.
Okay. So
Because,
like,
you know, if I put this 100 Newton force up,
okay.
then that would make it rotate this way,
Right.
and that would be the negative Y.
Got it.
Okay?
Thank you.
Sure. So it's always nice to have ways to convince yourself that your answers are right, that you didn't just punch something in wrong. And this, I think, is a helpful intuition to make sort of natural. So I would try to do that a little bit. You don't have to do it all the time, but keep sort of working on that intuition. Okay, that's all. Okay, the next thing that we're going to get into is the biggest topic in this class, the most important topic in this class. It's the one topic I would say, like, if somebody was asked, some random professor in Idaho was asked to give you a problem to see whether you know statics or not, they would give you this type of problem. This is structures. And a structure is a collection of bodies connected by joints. In static equilibrium. What's it called if you have, you know, you can connect bodies in such a way that they can still move. So what do you call a collection of bodies connected by joints that isn't in static equilibrium? So if it's not in static equilibrium, it's called a linkage. And we'll do calculations of those in dynamics. And I'm going to do this with, I'm going to sort of emphasize different things as I do this than textbooks usually do. So usually what the approach textbooks take is they break up structures into two categories. Those are trusses And for now, what I'm going to say about trusses is just that every member has two forces acting on it. And frames is the second category. And for frames, there is at most 2 members connected by any joint. Okay, there's 2 reasons why I don't really like just going straight to this. One is that 6 months from now or a year from now, my experience is that people don't always remember how to classify these things, and so they end up trying to fit the wrong kind of structure into the wrong category, and that's a problem, you know. And the second thing is, this doesn't cover every kind of structure. So there are a lot that don't fit into either of these 2 categories. Okay, so instead of doing these, I'm going to start and spend most of our time, almost all of our time, on structures, giving a single method that works for every structure, including the ones that don't fit into either of these 2 categories. So, okay, so we're going to learn one method. You don't have to classify it. And so you just apply it to anything. And it can be applied to things that can't be applied to either of these. So that seems good. The downside is, you know, there's a downside, and that's that especially trusses reduces the number of variables and the number of equations by a lot. So this method I'm going to teach you gets ridiculously unwieldy if you have large numbers of members in your structure. Okay, so we're first going to do this. We're going to spend a lot of time on it, and then I'll give you another approach where you're like, yeah, if you know it's a truss, you know, this can save you some time. But remember too that for now you're in school, like your whole world of engineering is being able to do stuff on tests or whatever. But like in a job, if you're trying to calculate a truss or any kind of structure, you're not going to be doing it by hand. You're going to be writing some computer program to do it, you know. And so I'll show you how to do trusses when we're done. You can do it if you ever need it on a napkin calculation or whatever. But really, this single method will give you everything you need to understand what's going on, and you can apply it later in computer programs or whatever. Question?
I was just wondering, so this process is essentially we just have to break the problem up because there's too many variables and not enough equations?
Yeah, so when we, let's see. So let me, I'm going to start by giving you the simplest structure I can, and we're just going to think our way through it, knowing what we already know. And then I'm going to give you a slightly simplified version that saves a little bit of calculating, so you're not losing any information or anything. But what we're trying to figure out when solving a truss, solving a structure in general, just means calculating all the external loads on every one of the members. So you're calculating joint forces and calculating, you know, yeah. So that's what we're trying to do. So, okay, the first question is, can we just think through think our way through a structure problem. So here's an example of doing that. And I just want to point out this isn't optimized yet. So once we do this, I'm going to give you an optimized set of steps. So when you see this in your notes, like when you're working on structures later and you go back to your notes, don't use this method that's not optimized yet. It just adds a lot of variables you don't need. Okay, so let's say our structure is, we have a pin joint over here and a pin joint over here, and this triangular structure makes an equilateral triangle. And let's use the simplest geometry we can. So we'll say all these lengths are 1 meter. And let's say that the mass of each of these two members, so M1 is equal to M2. And let's say that they're equal to 20 kilograms each. And might as well label these now. I'm going to call this body 1, this body 2. And then I'm also going to think about, so these pin joints, I'm going to think literally about what these pin joints are. And I'm going to call these pins bodies also. And I'm going to call this one body A, this one body B, and this one body C. Okay? So A, B, and C are the pins themselves. Like you could imagine, like if you tap it with a hammer, those come out, you know, and the thing falls down. And when I isolate those pins, I'm going to think of those as particles. Okay, in 2D, those are particles. I'm not going to worry about like the length of them, the thickness of them, or anything like that. Okay. So, okay, one by one, I'm going to do a rigid body analysis on each of the two bodies. And then as needed, I'm going to isolate the pins and do a particle analysis. And I'm just going to keep doing this until the number of equations catches up with the number of variables, you know? I mean, you're seeing it for the first time, so to you, reasonably, you just be hoping that eventually you do get the equations to catch up, you know? So, all right, so the first one is body 1. So let's think about what loads are acting on body 1. There's a weight force. It's 20 kilograms, so this is 196.2. And then at A, this body touches that pin A, right? So down here, and it makes a pin joint with it because it's a pin. So I'm going to call this a force vector, force on body 1 by the pin A. And then up here, what does it touch? Well, we're going to assume that it doesn't touch body 2. It only touches the pin, and then the pin touches body 2. Okay? So this is going to be the force on 1 by the pin B. And we're going to do a rigid body analysis. I'll call this the about point for this. the row force moment. And I'll start with the force F1A. The row vector is 0. This is 2D. The force vector is F1AX, F1AY, and the cross product is 0. Then we'll go to the weight force. Since this is an equilateral triangle, that angle is 60 degrees. So the row vector is going to be, if you went all the way to F1B, that would be 1 times cosine and sine of 60. This is halfway, so that's 0.5 times cosine and sine of 60. So that is 0.433.25. And the weight force is 0, negative 196.2. Could someone calculate 0.433 times 196.2 for me?
$84.95.
84.95. And then the last one is F1B. The row vector is 0.866.5. Force vector is F1BX, F1BY. And so the cross product is 0.866 F1BY minus 0.5 F1BX. Well, we can use that sanity check to make sure that the moment of our weight force has the right sign. Does it make sense that this would rotate the thing? It's negative, so clockwise. Yeah, that weight force would rotate clockwise around that pin, around the about point. So let's write out the equations we have. In 2D, we're going to have 4 equations. So the first one is the x component of Newton's second law. So that says F1AX plus F1BX is equal to 0. I'm just adding up all the x components of these. The second equation is the y component of Newton's second law. So we have F1AY plus F1BY minus 196 is equal to 0. Well, I'm just going to move that over to the other side of the equation now. So that's positive 196.2. And then the third equation says, I'm going to rearrange them just to match the order of the other ones so far. So I have negative 0.5 F1BX plus 0.866 F1BY minus 84 is equal to 0. So I'll write that as equal to positive 84.95. Okay, maybe we're done. Let's add up the variables and add up the equations. We have 3 equations because it's a 2D problem. And we have, 1, 2, 3, 4 4 variables. So 3 equations. Four variables. So we can't solve this yet. Come on, baby. All right, so now we'll just set these aside. The variables we have so far, just for bookkeeping, are F1A X and Y components and F1B X and Y components. So 1, 2, 3, 4 variables. And now we'll go to body 2. There's a weight force of 196.2 again. Down at C, the only thing that body is touching is that pin C. So here we have the force onto by C. And here, we're assuming that member 2 isn't touching member 1. It's only touching that pin. Okay, so we have the force F2B. Force onto by B. Okay? And now we'll calculate these forces in moments. Let's see, I guess I'll choose this as the about point up at the top. So the force F2B has a row vector of 0, force vector of F2BX, F2BY, and the cross product is 0. The weight force, this row vector is 0.433, negative 0.25. Force is 0, negative 196.2. And 84.95. So this is negative 84.95. Does it make sense that that force would have a moment that would cause a clockwise rotation? Yeah. And then the last force is F2C. Row vector is 0.866, negative 0.5. Force vector is F2CX, F2CY. And so the cross product is 0.866 F2CY plus 0.5 F2CX. And our equations, so our fourth equation says F2BX plus F2CX is equal to 0. Our fifth equation says F2BY plus F2CY is equal to positive 196.2. And our sixth equation says 0.5 F2CX plus 0.866 F2CY is equal to positive 84.95. So now we have 6 equations. How many variables do we have? We still have the ones from before, so we have F1A, and f1b and f2b and f2c. 2, 4, 6, 8 variables. So we're sort of heading in the wrong direction so far, you know? So is this ever going to work? Well, yeah. Now what we're going to do is isolate those pins, treat them as particles. We can reuse the variables we have here because of Newton's third law, and that'll let us catch these up, and then we'll be able to solve it. But this is as simple a structure as you can think of, okay? And we're going to come up with a system of 8 equations for 8 variables. So that feels like a lot of work for the simplest thing we can come up with. So I'll finish this next time, and then I'll talk about how to simplify this in a way that still keeps this method completely general. So it'll cut down the number of variables a little bit. And then we'll do that a million times, and then after a million times, I'll tell you how in some cases you can do simplifications that reduce the variables more. Okay, any questions? All right.